Mechanical advantage. Mechanical advantage, MA, is the force multiplying ability that machines provide, and it indicates the ratio of the resistance force to the applied, or effort, force, according to this formula. MA equals resistance force effort force. The MA tells you the number of times that a machine multiplies your input effort. This means that a machine with an MA of 4 multiplies the input effort 4 times. Thus, the ratio of input effort to output effort is 1:4, and the machine operator has to apply only 1. For as much force as he would if he did not use the machine. Let's use our formula to solve this problem. A man is using 70 pounds of effort to lift a 280 pounds box. To find the MA, this is what you do. MA equals R/E. MA equals 280/70. MA equals 4. In this case, the machine multiplied the input effort by 4 times, for a work ratio of 1:4. Clearly, it is easier for the man to apply an effort of 70 pounds to the machine than for him to apply an effort of 280 pounds to the box. However, because of the decreased input effort, the input distance must increase to accomplish the same amount of work, because according to the law of conservation of energy, energy cannot be spontaneously created. In other words, the man must back up and exert his 70 pounds of effort over a longer distance than if he just picked up the 280 pounds box. But by applying 70 pounds of effort over 4 times the distance, according to our 1:4 ratio, he can easily lift the box with only 70 pounds of input effort. A shorter work distance will require the man to exert more input effort. It sounds complicated, but it's not. Just remember that, on the exam, the question will give you all the information you need to easily solve the problem. Exam alert. Make sure that you understand how to solve for mechanical advantage, because it will be the formula that you will use most in the mechanical comprehension module. MA equals RE. Friction. Under normal conditions, some of the effort force goes to overcome friction within a machine. This affects your mechanical advantage and means a decrease in overall efficiency of the machine. Friction prevents any machine from producing as much work as is applied to it, which means that the work input is greater than the work output. The effect of friction in a pulley system is called drag, and you can estimate drag by finding the difference between the work input and the work output. Some of the test questions will ask you to calculate the actual mechanical advantage. Other questions will ask you to calculate efficiency, which takes into consideration the effects of external resistance, such as friction. But don't worry, the questions will give you the information you need to solve for the answer. Calculating efficiency. With any tool, friction impairs overall efficiency. If 75% of the input to a machine is available as output, and 25% is used in overcoming friction within the machine, then the machine has an efficiency of 75%. Because of friction, work input will always be greater than work output, meaning that no machine is 100% efficient. However, you can reduce friction by polishing surfaces that come into contact, using wheels or bearings between moving surfaces to allow them to roll past each other instead of slide, and lubricating the machine's moving parts. Simple machines are very efficient because they have few or no moving parts to produce friction. The efficiency of a well-designed lever may come close to 100%, and some inclined planes can have an efficiency of more than 90%. On the other hand, the efficiency of a block and tackle, which has several moving parts, can vary between 40% and 60%, and the wedge is the most inefficient of the simple machines because of the effects of friction. You calculate a machine's efficiency by comparing its work output to its work input and multiplying by 100, the ideal efficiency rate. Remembering that work equals FD, efficiency is the ratio of useful work output to expended energy input, such that efficiency equals work input times 100%. Therefore, if you have a work output of 125 feet-pound and a work input of 250 feet-pound, your efficiency will be 125/250 multiplied by 100%, or an efficiency rating of 50%. Exam alert. On the test, you will also need to solve for electrical efficiency, which is a little different from mechanical efficiency but operates on the same premise. You will use this formula: efficiency equals power input times 100%. So if you have a 10 HP engine that has a full output, but the engine itself operates at only 85%. Efficiency: what is the power input? You can use a diagram similar to the Ohm's law triangle, in figure 7.2, to reorient the problem. Because you are solving for power input, cover that value on the triangle to see what your equation will be. Now convert the efficiency rating to a decimal, 0.85, plug in the known values, and solve so that your problem looks like this. P I equals P/E. P I equals 10/0.85. P I equals 11.76. So your power input is 11.76 HP to make a 10 HP machine, with an efficiency of 85% run at its full rating. Principle of moments and torque. According to the principle of moments, you can maintain equilibrium, balance, if the moments forces tending to clockwise rotation are equal to the forces tending to counterclockwise rotation. These moments of force are called torque. When equilibrium exists, there is an equality of torque that is expressed by this equation. Weight of A, distance of A, equals weight of B, distance of B. Or FD equals FD. Figure 7.3 illustrates a platform balance. The clockwise torque is the product of the weight, resistance of A, 25 pounds, and its distance, 6 inches, from the fulcrum. A fulcrum is a point in the line of effort that changes the direction of the input effort. The counterclockwise torque is the weight of B, 30 pounds, multiplied by its distance from the fulcrum, 5 inches. According to the following formula, because the torques are equal and opposite, the lever balances. FD equals FD. 35 equals 25, 6. 50 is equal to 150. PO. EPI. In another type of problem, you might be asked to calculate how much input effort you need to apply to counteract an opposing torque. Figure 7.4 provides an example of such. 25 pounds. Torque motion. Torque motion.